Today we have Nemanja Antic from Northwestern, who's going to present to us his paper, Selected Facts, joined with Archishman Chakraborty. And the guest panelist is Rakesh Vohra. The format of this seminar is as follows. We have a 60-minute presentation with time for written questions from the panelists or also from the attendants. And we encourage the audience to participate. You can either post your question in the chat, or you can also add your question live. The talk is recorded. And before I hand over to Nemanja, let me announce that the next talk is by Males Pai, who's going to talk to us about taxing externalities without hurting the poor, with Philip Struck, and the guest panelists are Scott Commoners and Z. Young Kang. So the mic is yours.
All right. Thank you, Spiros, and thank you everybody for organizing and coming. I'm presenting a joint paper with Archishman Chakraborty, and he'll be here to answer questions in chat. All right, so story time. In the fall of 1945, there was a international relations crisis involving the US and Japan. And basically, the United States government was trying to insist that the atomic bomb didn't cause any radiation issues. To back this up, they had provided actual studies in both Japan and earlier testing in the United States that showed that alpha and beta radiation was in fact low at both of these sites. And this was in fact true. However, as early as 1943, General Groves understood that gamma radiation might be, in fact, a significant problem here. But he kept this information sort of poorly distributed. It's not clear that the president, at the time he authorized the Hiroshima bombing, knew what the gamma radiation issue was. And so it wasn't until much later that the real facts of the situation came out. So this is a kind of environment where you have somebody who's informed, in this case, General Groves, advising a decision maker, the president, about a binary decision, dropping the bomb or not. And this can't be done just without any research. Okay, they had to do a lot of testing in New Mexico. And so it's backed up by actual measurements of radiation and the sizes of the blasts before that recommendation is made. But not all of the evidence is presented at the time the decision is recommended. And so this is the kind of environments that we want to study. You have a sender who's going to select a bunch of hard facts in order to persuade a receiver to accept a particular proposal. Okay, so in this case, to drop the atomic bomb. We're going to imagine that the sender is privately informed about all aspects relevant for the decision at hand and must reveal a certain number of indisputable facts. So we can think about this as applying to lots of environments. For example, newspaper editors, they don't totally make up their stories. The stories are often taken from AP. So they have some grain of truth, but they exercise power by choosing to promote certain stories and bury others. Or you can think about the sort of academic environment. We have, we choose which papers, when we publish our papers or we send our papers to journals, we choose which regression results to show and which regression results not to show. And so we're selecting certain facts in order to persuade a receiver, editor, or a referee to publish our paper. What I'm going to show you is a characterization of the sender optimal outcomes under commitment in this kind of environment. And we'll see that the most important sort of contribution is really viewing this problem as a maximum weight matching problem on a bipartite graph. And then after that, I'll talk about some extensions. For example, what can the receiver do, what rules can the receiver put in place in order to improve their outcome, given that we've been so far focusing on the sender optimal outcomes. And then other kind of examples, like what happens when there's limited commitment by the sender, or perhaps multiple actions instead of just binary actions. Okay, so if there's no questions, I'll just jump straight into the model. Okay, so the sender is going to know a state of the world X. Everything's going to be finite, but it's going to be arbitrary. The receiver is going to have some prior over the states, little x. And in each state of the world, there's going to be a set of facts, script f of x. The sender has to disclose one of the facts in the fact set corresponding to the actual state of the world, and then recommend a decision to either accept, which is d equal to 1, or reject a proposal d equal to 0. The sender's report, therefore, to the receiver is going to be a fact and a decision. It's going to be scrutinized by the uninformed receiver in the sense that the receiver is going to fully understand the equilibrium strategy that's used by the sender and then update in a Bayesian manner. Payoffs are also going to be quite.
Yeah, that went too fast. Can you go over it again? So sorry. So you disclose a fact, only one fact, right? This is an exogenous restriction on the technology of disclosure. Is that correct?
Correct. We'll see that one fact that I'll give some examples, but yeah, think about it as one fact. That's without loss of generality.
And then what does it mean to accept or reject a proposal? So sorry.
So the decision right now in the model is just binary.
I see. Okay. The sender, I see. Along with the fact, they also send a recommendation.
Correct.
I see. And then I see. So this is just formally writing down the 0, 1 and the fact. And so scrutinized by the uninformed. I see. Okay, good. Thanks.
Okay. No, please jump in. I tend to be too fast unless there are questions. Okay, so we'll see that the one fact is without loss of generality, but I'll explain that in a second.
Nemanja, can I ask? The F is common knowledge.
Correct.
Yeah. Mm-hmm.
Yep.
Okay.
It's understood what the fact set is. Okay, so payoffs. If the status quo decision, this d equal to 0, is taken, so if the proposal is rejected, everybody gets a 0 payoff. And then if the proposal is accepted, the receiver's utility from accepting the proposal is ux in state x, and the sender's utility is vx. It's going to be convenient for a lot of what I'm going to show you to assume that if the receiver wants to accept the proposal, then so does the sender. So that the sender is more keen for the proposal to be accepted than the receiver. So there are going to be 3 types of states we could partition the state space into. States where they both agree to accept the proposal. Everybody's payoff from accepting the proposal is positive in those states. States where everybody agrees to reject the proposal. Both parties have a negative payoff from accepting the proposal in that state. And then conflict states where the receiver wants to reject the proposal and the sender wants it to be accepted. Okay, so this is just assuming that the general is more keen to drop the atomic bomb than the president. Okay, and then there's an obedience constraint. Basically, the receiver weakly prefers to follow the recommended decision if his expected utility conditioning on the message and the fact that accepting the proposal was the recommended decision is weakly positive, and then he'll follow the decision to reject the proposal if his expected utility, given what he's observed, is weakly negative. And an important special case of this, and I'll use this in many examples, but we'll see that somehow understanding this case is the most important, is going to be one where the receiver's utility is just +1 and -1. So it gets +1 in the states where they want to accept the proposal and -1 in the states where they don't. In this case, the obedience constraint becomes a balance of probabilities kind of constraint. So now what the receiver cares about is whether the probability of the accepted set, which is a set where the receiver wants the proposal to be accepted, given the message, is at least a half, assuming a recommendation to accept the proposal. And then the probability of the acceptance set should be weakly less than a half if he's asked to reject the proposal.
So Nemanja, can I try to sort of figure out where we are within, I suppose, well, other models that we've seen before? So you are sending a verifiable component, which is the X, the component for the F set, yes. And then you're making a recommendation, which is in effect completely unrestricted. In the sense that you could always recommend something that is completely inconsistent with a set of facts that you have. But you have to say one true fact, let's say, and okay, so there's not a lot of structure here, right? There's
no,
yeah,
and in fact,
okay.
It's going to encompass standard sort of persuasion environments where you don't actually reveal any facts as a special case. I'll explain that in a second, but you could imagine one possibility, if we go back to the fact set, is that all states in the world have the same fact in the fact set. And so then disclosing that and then the receiver updating on that information doesn't give them anything.
Okay. Yeah.
Yes.
Okay. Okay.
So I'm trying to understand the reason why you have this recommendation on top of the fact. Is it an equilibrium selection thing, or is there something? I mean, my understanding is that from the fact you should be able to sort of derive recommendation directly.
From the fact, no, not necessarily. So in the problem with commitment, I will sometimes want to commit to revealing the same fact. If I can't get my first best outcome, I might want to reveal the same fact, but give you a different recommendation.
I see. Okay. So
you commit to that so that you would listen to me when I tell you to accept the proposal. Otherwise, you won't listen.
Okay. Okay. Thank you.
Yeah. Just like in Bayesian persuasion. Okay. So an important special case of this sort of very general environment, as Francesco's pointing out, is going to be the Cartesian special case, and this is what Glaser-Rubinstein 04 focus on. So that's where the state space has this sort of product structure, and a state is just a vector of realizations for each of the dimensions. And then we can think about a fact as sort of revealing k out of these n dimensions. And so this is where sort of revealing one fact is without loss of generality. I can say that an allowable fact is only one, for example, that reveals 5 out of the 12 dimensions or something. Does that make sense? So an allowed fact will have to give me 5, for example. Okay, so just to give you an example of what a Cartesian case might look like, here is a 2-dimensional, so this is n equal to 2 case with k equal to 1. And what I have in the curly braces here are the fact sets. So what's an allowable fact? You have to tell me if the x dimension is either left, middle, or right, or you can tell me whether the y dimension is up or down. And if this is the realized state of the world, if it's m up, the only facts you can reveal are middle and up. You can't reveal facts outside of that. Does that make sense? So these are the kind of examples, and in fact, I'll return to this example. These are the kind of examples I'm mostly going to be focusing on. But I just want to show you that it can be generalized quite a lot given the structure. So here's an example where there's some hard evidence and some soft information. And then what can be revealed in different states can be quite different. So think about, this is a 3-dimensional example. Think about sort of a war in Iraq and the rationale for going into it in the first place. And there might be three things you care about: the size of the Iraqi conventional military, either large or small, whether Iraq has WMDs, yes or no, and then the mood of the regime, whether it's peaceful or warlike. What can you actually have hard evidence on? Well, there's absolutely no way you could have hard evidence on the mood of the regime. That's not in any of the evidence sets. You could probably get very good information on the size of the conventional military. Okay, there are ways to figure out how many tanks they have and whatnot. These are things that are sort of much more easy to observe by satellites. And so in all of these fact sets, the size of the military, large or small, is an available fact. But then we come to WMDs, which is kind of a mixed thing. If WMDs are present, it's possible for Iraq to disclose, yes, we have WMDs. That's something we can disclose if we choose to. But if there are no WMDs, it's not credible to disclose, I don't have WMDs in this example, because it could be, I guess as it was in this case, interpreted as they're just choosing not to disclose versus I'm really convinced that they don't have them. Does that make sense? Okay, so this is a kind of structure that's going to be allowed by our environments. It's just, I'm not going to give examples that are this complicated. All right, so what do we actually do? What's the timing of the game? Well, the sender is first going to publicly commit to a strategy. A strategy is just going to be a mapping from states to messages, and is going to try to maximize his expected utility ex ante, subject to the obedience constraint. After that, nature is going to draw a state, and then we're going to draw a message according to the strategy of the sender. The receiver updates on everything and decides whether to follow the recommended decision. Okay, so the timing here is a little bit different to Glaser and Rubinstein. Glaser and Rubinstein are focused on, this is a paper that's inspired us and very much related. And I see that Max has already asked a question about it. So there, it's sort of more a mechanism design problem where the receiver first sort of commits to a set of rules for persuasion, and then the sender follows through on the mechanism. Our version is sort of focusing more on the sender optimal outcomes and sort of looking at the sender committing to a strategy first, and then the receiver updating. And one of the questions that we're going to focus on, the first question, in fact, is going to be the notion of subversion. Okay, what is subversion? The dictionary definition is the undermining of the power and authority of an established system or institution. For us, what that's going to mean is that the receiver, even if they have decision-making authority, doesn't get what they want. In fact, the sender gets what the sender wants in all states of the world. And so our first results are going to be characterizing necessary and sufficient conditions for when subversion is possible in this environment. Okay, so let me give you an example of subversion and give you an example of the kind of pictures I'm going to draw. If you haven't followed the notation so far, don't worry. This is the slide to come back to and sort of figure out what's going on. So we're going to have 2 dimensions, like I introduced before. The x dimension can be left, middle, or right. The y dimension can be up or down. And I'm just going to choose a uniform prior for now. Okay, so given that we understand it's uniform, I'll remove that information and let me tell you the payoffs of the receiver. The receiver's preferences are going to be -1 on some of the states where they don't want the action, the proposal to be accepted, the atomic bomb to be dropped, and 1 on some other states where they're happy for that to happen. I'm going to assume that the sender's preferences are the following. The sender always agrees with the receiver when the receiver wants the bomb to be dropped, but they are sort of more keen to do it. So in these states, MD and LU, the sender wants the proposal to be accepted, the receiver doesn't. And then in the state LD, they both agree that the bomb shouldn't be dropped. So I'm going to color the states as follows. The blue is going to indicate that everybody agrees to accept the proposal. The red is going to mean that everybody agrees to not accept the proposal. And yellow is disagreement or conflict. And the conflict in this case is sender wants the bomb to be dropped and the receiver doesn't. And so you'll notice that for these examples with +1, -1 utilities and everything uniform, the colors capture all of the notation. And so what I really want you to remember here is what the colors mean. Blue states, everybody agrees to accept the proposal. Red states, everybody agrees to reject. Yellow, there's a conflict. Sender wants acceptance, receiver wants rejection. And because it's uniform and the utilities are +1 and -1, what does obedience mean? Obedience is achieved when one of these yellow states is pooled with one of these blue states. Is that okay? That's because the status quo decision gives you 0 utility, and with uniform, matching one or pooling one yellow and one blue state will get us obedience. All right, so here are those fact sets again when k is equal to 1. So in each of these states, I can reveal either the x dimension or the y dimension. I can have another case, for example, when k is equal to 2. Here, the fact sets are different for each state. Basically, I have to reveal both dimensions. That's the only allowable recognized fact. And so if the state is MD, I have to tell you that that's the state. Okay, that's also a special case of the model. Finally, I could have a special case where I reveal absolutely nothing. You can think about this as k equal to 0. All states have an allowed fact, which is just the empty fact. And it's in fact this version that corresponds to standard Bayesian persuasion.
Nemanja, just very quickly. So when you're showing these three things, I should think of these three as exogenous restrictions on the technology, right?
Yes.
Which I interpret as hardness or softness, right? So this is an exogenous restriction that you can or cannot disclose these type when you're wearing the K, that is, right?
Correct. I will, if I have time to talk about the rules of discourse stuff, this is where the receiver can sort of make certain requests of the sender.
Yeah, but for
right now, it's very helpful just to think about these as exogenous restrictions.
Okay, yeah, that's the technology.
Yeah, exactly.
But if I may, with one point, it could be also greater than or equal to k. So there could be a situation where I have to give at least some evidence, but I can give more evidence if I wish to. That's also allowed.
Right. That's not going to play a particularly important role under commitment, but again, if I have time to talk about lack of commitment when incentives play a role, that can be quite important.
Yeah, so that's covered too in terms of the restriction.
Can I just see if I understand in this precise example with k equal to 0, when you say this is equivalent to Bayesian persuasion here, is what you're saying is that I will commit to a revelation strategy where I'm not gonna say blue when the state is in fact yellow or blue, and say red when the state is red. I will mix. I won't. In other words, I won't be necessarily truthful about my recommendation given the states. I will mix. I will sometimes, try to get you to accept the proposal when we are in fact in the yellow state. I can, because I have commitment power, I can do that. If I'm doing cheap talk in the sense that I'm not committing here where you have no information, no hard information available to provide, presumably what we're going to get is that pooling, I mean, there's not going to be any meaningful information transmission. I don't want. Does that make sense? Is that right?
Okay, yeah. So here, what happens for Bayesian persuasion is I'm going to reveal this null fact regardless of what the state is. And that's sort of true in persuasion settings because you don't reveal any hard evidence ever.
Mm.
You don't have to reveal any hard evidence. And with binary actions like this, it suffices just to recommend an action that's sort of the optimal or an optimal strategy. And so what the persuasion outcome here would be is that in these 5 states, the yellow and blue states, the receiver will conduct an experiment that recommends the proposal be accepted. And then in the red state, the experiment will just recommend the proposal be rejected. And so,
so you're doing the usual modification of a prior to a different posterior by changing the so now it's becoming clearer to me what's going on is you're having essentially a Bayesian persuasion environment plus the possibility of also allowing for our hard evidence. This is
correct, and that's going to place constraints on the Bayesian persuasion environment.
Okay,
that's one way to think about what we're doing here is persuasion with certain kinds of constraints. And then, as Rohit was asking, those constraints are best thought of as exogenous for now. Okay, but the motivation is they come from some fact sets.
So they never help these constraints, the sender, I mean.
No.
They could help, right? Because
they will help when there's no commitment, or they can help when there's no commitment. In the case where you have commitment, they will not help. They can only hurt. Okay, so I'm going to represent these yellow and blue states as a graph, and that's sort of the key thing I want to get across here. Just to sort of recap, with commitment, the sender can always get what he wants in the red states, can always recommend the reject decision, can always get what he wants in the blue states, can always just commit to recommending the accept decision only on the blue states. And so really the question is, how many of these yellow states can the sender get what the sender wants? Okay, that is, how many of these yellow states can be pooled with some of these blue states? Okay, and if our evidence structure is like this, that is, anything can be pooled with anything because all states share a common fact, we could represent this as a graph, as a completely connected graph, as follows. There are the 2 yellow states, left and up, middle and down, and those states can be pooled with any of the 3 blue states, middle up, right down, and right up. So for example, this would be a pooling that's possible when k is equal to 0. I could pool states middle down and right up, and states left up and right down. However, let's look at the evidence or the fact sets when k is equal to 1. Okay, now the constraint starts to bind. I have to reveal one fact when I make my recommendation. So previously, the proposed strategy was pooling the states pooling state left up with state right down. But if we look over here, the state left up has allowable facts left and up. The state right down has allowable facts right and down. Those states share no facts in common. And so if I have to reveal a piece of hard evidence when I make my recommendation, there's no way I can pool those states. Okay? Similarly, middle and down cannot be pooled with right up. But this state, middle down, can be pooled with right down because they share the y dimension in common. They have the y dimension in common. Or it could be pooled with middle and up because it has the x dimension in common. Does that make sense? So this evidence structure then is going to allow us to create a graph where the edges of the graph indicate states that can be pooled together given the fact sets that are available. So the fact sets are going to determine where I draw a link. There's a link here between the state left up and middle up because the y dimension is the same and I can reveal the y dimension. Same thing here, middle up is connected to middle down because I can share the X dimension is middle. And so then I can ask, okay, how many of these yellow states can I pool with blue states? Okay, and the question is again the same. Can I get all of them if we're looking for subversion? Can I pool all of the yellow states with some blue state? And in this case, it's still possible. So here's one way to do that. Okay, so I can send message M1 if the state is MU or MD. What's the actual message going to be? It's going to reveal that the X dimension is M and that you should accept the proposal. I could send another message if the state is LU or RU. It's going to reveal that the Y dimension is up and that you should accept the proposal. And if the state is RD, I could, for example, reveal that the X dimension is R and that you should accept the proposal. And this would get what the sender wants in all of the yellow states. Okay, let's take it one notch up. So suppose now that k is equal to 2 and the sender has to reveal both pieces of information to the receiver. Okay, well now none of these states have facts in common. And so if I draw that as a graph, it's just completely disconnected. And so no pooling is possible. Obviously, the sender can't get what he wants in these two yellow states. So this is an example where subversion is not going to be possible. Okay, so the big kind of takeaway here, the big lesson is that one can view this problem, the problem of the sender finding the optimal strategy, as a matching problem on a properly drawn graph. And so the idea is we want to match as many of the yellow C states to the blue acceptance states as possible. And so from matching theory, we have a very old result due to Hall 1935. A C-perfect matching exists. So C-perfect matching is a matching that matches all of the yellow states to something, if and only if the number of, for any subset of the yellow states, the size of that subset is less than or equal to the size of the neighbors of that subset. The neighbors here are just the states which can be matched to one of those yellow states, the blue states that can be matched to one of those yellow states. Okay, so this is all well and good. It works very cleanly if we have uniform probabilities and we have uniform priors and we have +1, -1 utilities. So how do we extend beyond that? But let me pause here, see if there are any questions.
Can I ask one question? So
Yes.
Can you think of the way that you describe the fact seems to me that it's like also like having a partition of the state space, and then you have two different partitions, and then you can reveal different partition cells. Is this? I mean, it's probably a different terminology, but just for me to understand.
I'm having a lot of trouble hearing you, Spiros. I'm not sorry.
Can you hear me better now, or not?
Yeah, a little better.
I want to ask you. Sorry. So can I think of the facts as having a partition of the state space? And then I reveal a partition cell. So this would be one fact. So when k is 1, is essentially I'm choosing one partition and I'm choosing one partition cell and I reveal that. Or if I have k equals 2, I have two partitions and then I can reveal the true state in some sense in this example, because I reveal both the one dimension and the other one.
You reveal two partitions. Okay, so you can definitely think about the graph structure sort of partitioning the state space in a particular way, but I don't know about revealing two partitions. I'd have to think more about that interpretation.
Okay.
Okay. All right, so what happens, here's an example, if we don't have uniform priors and we don't have -1 +1 utilities for the receiver. So in particular, I'm going to have more weight, a bigger prior on this yellow state, middle down. I'm going to have a larger negative utility on this state, left up. And then I'm going to have a larger positive utility on the right up blue state. Okay. Again, I've chosen this to keep things easy, but the idea is going to extend to any kind of utilities and priors as long as, well, everything is rational. Okay, so what can I do? The trick is going to be to sort of split up these states or to clone these states into pieces that are equal and that are comparable. So if you sort of look at the weight or the worth of this state, it's sort of the negative expected value for the receiver is kind of twice the positive expected value of this blue state. And we can calculate basically the weight of each of these states just by multiplying the P and the U together to get these weights. And so if we take 1/10 as our base, we can imagine this problem as one where this yellow state, the left up state, is kind of worth 2 regular states. This is also worth 2 regular states. Here it's because the utility was worse. Here it's because the prior was higher. And then the blue states are just, given according to the weight. The top right blue state is heavier because, again, the utility was more positive here. And so we can now, with non-uniform and non+1 -1 priors, clone states in a way that if I think of the LU state not as one state, but as 2 separate clones of it.
Sorry, Nemanja, sorry, I'm very slow. So why is there a 0 on the red? Sorry, because you want to...
because I don't have to worry about
it.
So I'm never going to worry about the zeros. Yeah.
So then you're reweighing only the non-red thing and then asking, because these are the ones I want to implement. I see. Now I'm just I'm just ordering them in these numbers. Okay.
Exactly. No, thank you. Yeah. So the red state, I'm not going to worry about because there's nothing to pool with it, and the sender gets what they want anyway. The real question is how many of these yellow states can I pool with the blue states? And the thing I'm trying to emphasize is that in order to get what I want in this yellow state, I can't just pool it with one blue state. I'd have to pool it with this blue state and then a little bit more. And what I'm effectively looking for is a sort of greatest common divisor kind of thing that determines how many of these clone states I want to sort of split each of the actual states into, so that a clone state here and a clone state here or here achieves the obedience constraint for me.
Nemanja, can I ask a question here?
Yes.
You're still keeping this V as -1 +1 when you are doing this example, right? The sender's payoff.
Correct, but because here the sender is getting what the sender wants in every state of the world, what really matters is the sender's cardinal payoff. Ordinal payoff, and not the cardinal payoff. So it could be anything else for the sender.
Can I also ask a question about this thing? So what you're doing here, you're taking the states that have the lowest weight, you're making that equal to 1, right?
Yes.
What then? But it just so happens that the weights of the other states are twice as that, so you give it 2.
Yes.
If you had more variety of weights, would you just order them ordinally, or as I'm guessing, you would have a cardinal? So given it needs to be cardinal, correct?
It needs to be cardinal. So I'd look at kind of the biggest fraction that divides all of these weights, and then I'd weigh each of them. So you might end up with 3 clones of this state, 7 clones of that state, and so on.
Right. So you could have a sequence where the numbers are 2, 3, and 5.
For example, yeah.
For example, okay. Where 2 is the smallest because, you can't give necessarily 1. Things may not be just exactly twice or 3 times. So in order
Exactly.
you're finding a common unit of measure. Yes, yes, yes.
And as long as everything is rational, such a unit is going to exist. And if you're worried about rationality, we have sort of approximation results.
Okay, okay.
If you want stuff to be irrational. Okay.
But clearly the cardinality still matters because you need to take into account probabilities and things like that. Yes.
Correct. But these weights,
Mhm.
so Arda's question was about the sender's payoff, the V. These weights are totally based just on the prior and the receiver's payoff.
Yeah.
So for drawing these weights and doing the cloning trick, all that matters is the receiver's cardinal payoff.
Mhm.
Okay.
Yeah.
Not the sender's. Okay. So we can then, once we've figured out how many clones we need, we can then do the same graph that we've just done, except that we're going to have two clones of each of these states and one of some of the others. And then each clone is going to be linked to whatever or connected to whatever the actual state would have been connected to. So the LU state, in this case, has two clones. And each of those clones can be matched with the MU state, or one of the clones of the RU state, or the other clone of the RU state. In this case, for all of these, you would be revealing that the Y dimension is up. And then the MD states state has two clones, and those can either be matched to MU or RD. Okay, so we can again ask, is there a C-perfect matching here? Can I find a matching that matches all of the yellows to some blues? And the answer here is yes. So here's such a matching. You'll note that this matching now requires a little bit of randomization. If the state is MD, with 50% probability, we're in the sort of left clone here. And in this case, we're going to reveal the X dimension is M and match it with state MU. And with 50% probability, we're going to reveal that the Y dimension is D and match that with the state RD. And then LU and both clones of LU are going to be matched with both clones of RU here. Okay. Okay, so we've sort of already described this trick of cloning in general. We're going to assume these weights are rational. We can find a highest common factor for these weights and then create the right number of clones. And if we do that and add everything up correctly, we have our sort of first result. So again, if we let NS denote the set of neighbors of a subset of the yellow set, so these are the blue states that the yellow states could be share a fact with, then whenever PXUX is rational, a subversive reporting strategy exists if and only if the expected utility of a subset of the yellow states and its neighbors is non-negative for all subsets of these yellow states. And so it's sort of translating Hall's condition into the language of expected utility and the priors that we have. Okay, and as you already mentioned, or people have asked, this is independent of the cardinal preferences of the sender. Note that because the sender here is getting first best in every state of the world, the same result is true with and without commitment. So I've been talking about the case with commitment, but if you can get whatever you want as the sender in every state of the world, then incentives to deviate are not an issue. Okay, so more interesting stuff happens when subversion is impossible. So in what remains, I'd love to talk to you about that. All right, so we're going to go back, and I'm going to give an example with uniform priors, and then just +1, -1 utilities for the sender, for the receiver, and the sender for, well, the sender I'll talk about in a second. Okay, so basic plain vanilla examples. The thing to remember is what the colors mean. We're trying to match one yellow with one blue in order to satisfy obedience. But here there are 4 yellows and 3 blues, and so the sender can't get what he wants in every state of the world. And so here, to figure out the sender's best strategy, we want to think about the sender's preferences, in particular on these yellow states. So we're going to give the sender some V's, state-dependent utilities, from having the proposal accepted in the different states. So I've just picked some numbers here, 2, 1, 3, and 4. The blue states, the sender gets what he wants anyway, so that doesn't really matter. The red states, the sender gets what he wants anyway, so that doesn't particularly matter either. Okay, so how can we solve this problem? The idea is again to represent it as a graph, but it's now going to be an edge-weighted graph. And in particular, to each of these yellow states, we're going to assign a weight that corresponds to the increase in the sender's expected utility if the sender is able to match this particular yellow state with some blue state. So each of these, so the state -1, 1, the top left state, occurs with probability 1/9. It gives the sender extra 2 units of utility if the proposal is accepted there. And so it carries a sort of expected utility weight of 2/9. Does that make sense? And so now the question is, can we figure out what is the maximum edge-weighted matching on this graph? And that'll be the sender's optimal strategy. That's the result. And so this problem is well studied in sort of operations research and matching theory. I learned about it first from a talk by Rakesh Vohra and some lecture slides that he has on his website. And so I don't know if he's here, but it's always nice to see how economists might use similar concepts. So I won't given the time, I won't take you too much through the linear program, but basically the main kind of result here is that once we're in a clone in the clone space like this, there is a pure strategy solution to the linear program. And it's important that there exists a pure strategy solution because when we think about a matching, you either match along a particular edge or you don't. So it's either a 0 or a 1, which is a pure strategy. And so in general, for our problem, when it's not in the clone space, there will be no pure strategy solution. We just saw in the previous example that sometimes you'd have to split a state into and do something different on each of the clones. But once you've cloned it in the appropriate way, there will be a pure strategy solution. And it's this that can be represented as a matching on the clone graph. And so this leads to sort of the main result of the paper, the main insight, which is that a sender's optimal strategy is a maximal weight matching on the edge-weighted clone graph as defined. The second part of the result, which is sort of not generally true in matching theory, and I want to talk about it if I have a few minutes, is that the maximal weight matching must also be a maximal cardinality matching. Okay, this is going to get us quite a bit of robustness in this problem and is going to play an important role in some of the applications. Okay, so the first part of the result, the maximal weight matching, is very much going to depend on the sender's preferences, and the cardinal aspect of the sender's preferences V. The second part will not, and that's quite helpful for characterizing the receiver's payoffs. Okay, the first part of the result is nice because we can use well-established algorithms like the Hungarian algorithm to solve this problem. I won't take you through this now, there's just no time. But what the algorithm delivers here is the kind of matching you'd suspect for the example that I've given you. So this top left yellow state will be matched with the top right blue state for a sort of increase in payoff of 2/9. This blue state will be matched with the bottom yellow state, increase in payoff of 3/9. The yellow state in the bottom right will be matched with the blue state just above it for an increase in payoffs of 4/9. And then this middle yellow state will be unmatched. And that sort of makes sense because that was the least valuable state for the sender. And in this case, that ended up being possible. This may or may not be possible depending on how the states line up.
I'm sorry, I might have missed this. Are you matching always? You can mix on one side and two states on the other, or 3, 4, whatever states on the other, right? Yes.
Yeah, so here there's no reason to do that because I've chosen a uniform example with +1, -1 utilities to sort of give a simple example that doesn't have any of the cloning.
Okay.
So you don't need to do that. And there's an optimal solution where you don't. Okay, so in the interest of time, I'm actually going to skip the second part of the proof, the proof of the second part of the statement, which shows that the maximum weight matching in these problems is also maximum cardinality match.
Can you spend 30 seconds explaining what that means? Sorry, like, so it's like, I'm still trying to understand your claim and then the robustness aspect of it. So what is that maximum weight matching is maximum cardinality matching? Like, what does it mean?
Okay, perfect. So, okay, here is a, thank you. Here's a sort of arbitrary problem. And here's a potential matching on it. So this yellow is matched with this blue, this yellow is matched with this blue, this is matched with this, and this yellow here is unmatched. And so this is not a maximum cardinality match because there's another matching in which all 4 of these yellows are matched to something. For the kind of problems with the preference structure that we have, this is not going to be a maximal weight matching. But in general, it could be. So if the weights were different, the special structure here comes from the fact that each of these yellows has the same number. In this case, this yellow has a 2 associated with it always, this one a 3, this one a 4, this one a 1. If that wasn't the case, if I made some of these, for example, if this was a 33, this was a 22, this was a 100, now the green matching here that's highlighted would be a maximum edge-weighted matching. Okay, why? Well, if I was to try to match this yellow to something, it would either have to go over here, in which case I'd gain utility 4, but I would lose this thing which was giving me 33 utility, so that seems bad. Or I'd have to go over here, in which case I'd miss out on this link, but that was giving me utility 100, and I'd be gaining utility 4, so I don't want to do that either. And so this, for other kinds of edge weights, might actually be a maximum edge weight matching with which these algorithms would deliver for me. What I'm saying is that because of the structure of where these edge weights come from in our problem, okay, these are not 22, 33, and 100. They're 2, 3, and 1, and in particular, they're all the same across. I can come up with what's called an augmenting path, which I'm going to draw for you here in red. And now, if I think about replacing the green edges of a match with the red edges, I'm only increasing my edge weight and I'm increasing the cardinality. So if you sort of just play along, if you go from here, this 3 on the red edge is replacing the 3 on the green edge, so there's no loss. This 3 on the red, this 2 on the blue edge, on the red edge is replacing the 2 on the green edge, no loss. This 1 on the red edge is replacing the 1 on the green edge, no loss, but I'm also adding another edge, which is a 4. And so I've increased the weight and I've increased the cardinality. But that's true only because of the special structure. It would not be true and is not true in general. Does that make sense? All right, so
Nemanja, sorry, where you're going very quickly. You're telling us essentially when some yellow states don't matter, you just forget them, and it's optimal for you to just stop trying to get them to take the right decision there, because you need the receiver to take the right decision in other yellow states that are much more profitable for you. That's the logic. But now, can you go back to the proposition? What this is saying is whenever, what is the
Sorry, the
second part
proposition
of a
is,
result?
sorry.
Sorry. Okay. So when is it that we're not, we want to use all the yellow states basically? When is it that we want to do this on all the yellow states? The example you gave, intuition, is when all the states are kind of equally important in some way, or closely, similarly important. There's not a huge gap between them. Is that right?
We want to use all of the yellow states if we can. It's going to
Yes.
turn out that we're going to want to always use as many of the yellow states as we possibly can.
Yes.
Okay, this is because of this preference structure. That's the second part of the statement.
Okay, that's the second part of the statement.
We're going to
So-
try to always use as many yellow states as we can.
Okay.
And the point is that's not generally true in these problems of edge-weighted matchings, because if some edges are worth a lot more than others, like this example I just showed you,
Mhm.
then you wouldn't want to do that. You would
But
want
it's
to.
always true in our problem, right? It's always true in today's paper.
It's always true in today's paper. No, I'm just showing you why there's something to prove here and why it's not.
So I guess what I'm missing is what. So this example seems a legitimate example to me. I guess you guys are saying we're making an assumption that's excluding this example, and that's what I don't understand.
Correct, because in the way that we've motivated preferences, the sender doesn't care which blue state a particular yellow state is matched with. It's always the same increase in the sender's payoff, because the sender just gets a marginal utility increase from having a yellow state matched to something, not having a yellow state matched to a specific thing.
Okay.
So you could imagine a different kind of story where what I match a yellow state with, if I match a yellow state to a particular blue state, that's somehow more valuable for me.
Mm-hmm.
Maybe it's easier for me to make certain kind of arguments because certain facts are more closer together.
Okay.
And then I can
Okay. Now I understand. Okay.
then I can get this kind of structure. But for the purposes of today's talk, we don't have that generality.
Okay.
So whatever you match, the sender has a state-specific utility, and whatever state that whatever blue state that yellow state is matched to, it's worth the same. All right. How much time do I have? A few minutes. Okay, so what's nice about this is that it allows us to characterize the receiver's expected utility in this problem in a quite sort of neat way. You can think about it as having two components. The first is just assuming that the sender gets what the sender wants in all states of the world. So in particular, that the sender, for all of the blue states and all of the yellow states, implements, has the proposal accepted. And then the second component is what you can think of as the Hall deficit. It's the maximal subset of yellow states that don't have enough blue states to be paired with. And you're looking at I guess this is the gain in expected utility for the receiver from those states not being matched. And it's looking at the largest yellow state set that will not be matched to some blue states. In the previous version that I showed you, the resultant subversion, well, the condition is that basically this maximum is 0. And in that case, we just have the first part of the receiver's utility, which means just the sender gets what the sender wants in all states of the world. And now there's the second component, which is looking for the largest yellow set, and then the expected utility gain from that set not being matched. Again, what you'll note here is this is independent of the sender's strategy and also the sender's cardinal preference. It matters, of course, what the A and the C states are, but the cardinal preference of the sender doesn't matter for characterizing this. Okay, we can also characterize the sender's payoff. In general, it's just the weight of the maximum weight matching, but for some special cases, it's going to have a nice closed form that's a bit like this too. All right, I'm sort of running short on time, and so I have lots of topics I could talk to you about. So we should choose. Would you like to hear about limited commitments, some rules of discourse, multiple actions?
I mean, you have a few minutes more because we asked a lot of questions, so maybe you can take a few more minutes, I think.
Okay.
Another 5
And also the role of evidence, I would say that's probably because we haven't done any evidence yet, right? You're keeping K equal to 0 right now.
Oh no, this is applying to all kinds of K, right?
Okay. But I suppose I was asking about the increasing K, this result. Yes.
Okay, sure. Yeah. I didn't say it. Very good. Thank you. So matching yellow states to blue states becomes easier the more links there are in a graph. So as soon as you increase K, you're going to destroy some of these links. This was the case with K equal to 0. This was the case with K equal to 1, fewer links, K equal to 2, even fewer links. And so anything that destroys edges in a graph like this is going to make subversion more difficult. Anything that adds edges is going to make subversion easier. And so adding more requirements on evidence is typically going to be good for the receiver. One of the things the receiver would ideally want to do is force the sender to reveal all of the dimensions relevant to the decision if possible. Okay, and you could think about, in reality, why that may or may not be possible. Okay, let me give a quick example on limited commitment, because I think this is quite interesting, and this is sort of where the matching theory that we're aware of sort of stops. And I think there are interesting questions to answer, both interesting economic questions, but also interesting mathematical questions. So with limited commitment, everything we've said about subversion holds trivially, which I've said. So interesting case is what happens when there's no commitment to anything. There's no commitment to the evidence I'm going to disclose to you or the recommendation I'm going to make. So just going back to that earlier example, the Hungarian algorithm involved matching this top yellow state. These matches are in green. Okay. And I want to argue for you that this is non-incentive compatible. Okay. Why is that? If the state 0, 0, this middle state is realized, this middle state could reveal the fact that the X dimension is 0 and could recommend the accept decision. And you'll note that with the matching with commitment that's proposed is that this bottom yellow state, the 0, -1 state, and the 0, 1 state, they also reveal that the X dimension is 0 and they recommend acceptance. And so without commitment, this middle state would actually just copy that strategy by the 0, -1 and the 0, 1 state. Okay, but consider the following matching. This will now be incentive compatible. So the 0, -1 state is still matched to the 0, 1 state. The 1, -1 state is matched to the 1, 1 state. And now the 0, 0 state is matched to the 0, 1 state. So let's think about what evidence is provided on the equilibrium path here. Either X is equal to 0 is revealed, X is equal to 1 is revealed on path, or Y is equal to 0 is revealed on path. Now there's an unmatched state over here, unmatched yellow state, -1, 1, but that state can't reveal any of the evidence that's revealed on path. It can't reveal that X is 0 or X is 1, and it can't reveal that Y is 0. And so this is now going to be incentive compatible for the sender, and you'll note that in general which is not surprising, commitment sort of has an advantage over the case with incentives. In particular, the sender can no longer get what he wants on this more valuable state in the top left corner, but now gets what he wants in this middle state. Okay, the way so we're not aware that matching theory uses these kinds of constraints, but I think it would be a very interesting extension of these models. And so we have some ideas about how what these constraints mean. What they sort of say is that if there is a state that is column matched, like we had here, this yellow state was matched in the column, then any other yellow states that share that column, that can mimic that evidence, have to be matched somewhere. And similarly for things that are row matched. Okay, thou shall not covet, matches in the same column as you or matches in the same row as you. All right, I'm gonna skip this, which is a little bit unfortunate, about the receiver's rules of discourse. Here, we change the timing, so we sort of assume, suppose the receiver can commit ex ante to only allowing certain facts to be reported. Basically can ask, if we go back to that original example, the president insists on hearing only about gamma radiation and doesn't care about alpha and beta radiation. How do you choose what fact to ask for? Okay, and here it's very helpful that we have this characterization that's independent of the strategy and the preferences of the sender, the characterization of the receiver's utility, and so we can kind of characterize the receiver's optimal rule of what evidence to ask for a large class of sender preferences and independent of sender strategies. But maybe in the last couple of minutes, what I want to introduce is a little example or a little extension to multiple actions. So again, another application where this kind of thing is relevant is, think about a classic proposer-vetoer model in political economy. So you have an interested party who wants to change a status quo policy to something else, okay? Suggests an alternative policy to Congress or the president, and then the choice that the decision maker has, the receiver has, is just keep with the status quo policy or accept the alternative policy. We can imagine the status quo policy is our decision to reject the proposal, as we've been looking at it so far. But then we can also think about the sender now proposing any other policy that's positive, and then choosing what policy to recommend as an alternative. And so one specification might be that the preferences of the sender are just D times the utility from accepting the proposal in a particular state, so that it's multiplicative in this way. Preferences of the receiver are, of course, also going to matter, and if they're also linear, this is a typo. Preferences of the sender, of course, V and not U, so this should be a V. Preferences of the receiver, if they're also D times U, then nothing is going to change. And so it's sort of more interesting to look at the case where the receiver's preferences are, for example, +1 when D is positive and they do the right thing. So they get some sort of known benefit from changing the status quo in the right direction. But the cost of changing the status quo in the wrong direction is proportional to the action that's taken. Okay, so taking a more extreme action, if it's wrong, is more costly for the president than taking a sort of less extreme, smaller action, an action closer to the status quo. And so then what can, in this case, the Just to clear all, yes, okay. What can, in this case, the sender do? Let's go back to that example I've been showing you over and over again. Well, the sender really cares about getting high actions in this yellow state that's worth 3 and this yellow state that's worth 4. And so here the sender can commit to the following kind of matching. This was what it was before. Under these preferences, the sender can commit to matching this yellow state with 2 blue states. And what that's going to allow the sender is, in this very valuable yellow state, the sender can actually get a more extreme policy implemented. The proposer can propose dropping a very big bomb, for example, in the rightmost states, and that's very valuable for the sender, and dropping a sort of intermediate-sized bomb in the 0, -1, and the 0, 1 states, and then not dropping any of the bombs in the other states, not having any proposal accepted. In this particular specification, a greedy kind of algorithm can be used to deliver the optimal outcome. Actually, it's quite simple with these particular receiver preferences here. Okay, we can talk about other extensions. One thing I want to briefly mention is what happens if there are 2 types of conflict. So think about there being potentially conflict of the other type, where sometimes the sender wants to reject the proposal, but the receiver wants to accept it. Our results on subversion are going to go through, except now we also need to look at a graph that's induced by the red states being matched with the conflict states of the other type. And so then the equivalent characterization is possible there. What's more interesting here is when subversion is impossible. And what's kind of nice there, which we haven't done, but I think is a very nice extension, is you can now match states of the 2 different types of conflicts together. So the C states can be matched with the CR states, with the new type of conflict. And when you start doing this, you no longer have a bipartite graph structure. But that's okay. Matching is well studied on non-bipartite graphs. I looked at Ricky's lecture slides on his website, and he has a chapter on non-bipartite matchings. And so this would be one application of something like that. And then another, I think, interesting extension, which where the math is which the math is well prepared to handle, are things that Francesco was asking about strength of arguments. So maybe some edges are more persuasive, more valuable than other edges. And that's something that you could easily incorporate into these environments. Okay, I will stop there. Take time for questions and comments.
Okay, great. Thank you very much, Nemanja. So before opening to the public, I don't know if Rakesh has any comments or questions.
Not at the moment. You have to give me time to warm up.
Okay. So any questions from others?
Oh, I don't know.
I'm trying to understand the F a little bit more. So when you can you say a little bit more when you said at the beginning that for now, let me think of it as fixed and so for instance, k greater than equal to 2, what you were saying, Archishman was saying, is that how does that work? Like, I'm just trying to understand how flexible is the theory for thinking a little more flexibly about script F.
I mean, script F is pretty arbitrary. It's just a set of things in each state that are verifiable. I think the Cartesian special case is a sort of nice natural example, and I've drawn a lot of examples, but this initial example is quite different to that.
So you're saying that as long, so the theory is very general along the dimension of restricting fairly arbitrarily the hardness constraints of facts, right? So that's really cool. I see.
Yes. What it's going to map to is if you have some arbitrary fx set, when it comes to drawing edges in a graph like this, let me go to the empty one. I'm going to draw an edge between a yellow and a blue state. If there is this state has a fact set associated with it, this state has a fact set associated with it. If they share a fact, an allowable fact, I'm going to draw an edge between it.
So I think to sort of, in the Cartesian case at least, the fact set for us could be defining that state. In the Cartesian case, it might help to think the set of facts that can be proven, shown, can be the definition of that state, the set of things that can be shown. That the soft information case showed that may not be the case because there could be addition. The state could have additional soft information, right? So you can't go back from the fact set into the state. So
right. So for example, different states here share the same fact sets.
But if
and that's allowed. What I didn't have time to talk about, and what I sort of skipped, is this notion of sort of rules of discourse, which is one way that the receiver might be able to improve their outcome, where for each state, they say, okay, only certain facts are acceptable to me. So I can kind of reduce the fact sets in a way that I choose, subject to a non-emptiness constraint. So I can't have states where there are no allowable facts, otherwise the strategies and things are not well defined. And then we have a characterization here about what it's stated here for the Cartesian case, but it sort of says what facts you'd want to allow and what facts you wouldn't want to allow. The characterization for the Cartesian case with k equal to 1 is you're going to choose just one dimension to allow, and you're going to allow all possible measurements of that dimension. So what I sort of quickly mentioned on this slide, the president asks for the measurement of the gamma radiation and only wants to hear about the gamma radiation and does not want to hear anything about the alpha and the beta radiation. Does that make sense?
And that's
so
regardless. That's regardless.
So now we're asking questions of the type of what, how might the receiver want to change the fact set to best improve their outcome?
Exactly.
Sorry, you were saying something.
No, and this is regardless of the sender he's going to encounter. These are sort of rules of discourse that are chosen before I know who I'm talking to.
Right.
So that's what so it's like rules design or so. Yeah.
Yeah.
Exactly. But it's independent of the sender's strategy and the cardinal aspect of the sender's preferences.
Right, because you do it before in some sense. So
you do it before. Well,
you don't have to, but you will.
You can do it after, but it's because of the second part of our main theorem. It's because the maximal weight matching is also cardinality matching, and that allows for a characterization of the receiver's utility that's quite independent of the sender's utility and strategy.
Very nice, yeah.
And so in these situations with the rules of discourse, different senders are going to choose different yellow states to match depending on their preferences. We saw that happens. They might have state-specific preferences that are quite different, but you're always going to want to put in place the same restrictions and ask for the same fact to be revealed to you, facts to be revealed to you.
Same dimension to be.
Same dimension in this particular case, yeah. I should say this is true. This result is, I didn't have time during the talk. This is true under full support. Without full support, it's a little more complex.
So basically, when you have the Cartesian product, you can only reveal dimensions, right? But then in a non-Cartesian product, you can have a more complicated structure, in some sense, sort of like partition that you can reveal different bits of the states, right?
Correct. And without full support, the non-Cartesian, you basically have a non-Cartesian structure, and then problems are going to be there too. Yeah.
Okay.
So I did have a question. In the paper, you mentioned that you allow for the possibility of the sender having access to a set of cheap talk messages. But then you also say it's not essential in that and I didn't quite understand that, because later on you say they're useful to deal with randomization.
Yes. Okay, let me explain exactly what we mean. This was one of the examples I sort of walked through. I don't know if you had followed this one.
Mm-hmm.
Okay, but let's look at this particular matching and think about sort of mapping that to a strategy. So if the state is MD with probability 1/2, you might match it with the state MU. Okay, and so you could, if you wanted to, just reveal the state of the world is the X dimension of the state is M, and you should accept the proposal. But if you wanted to sort of map it even more closely to the actual matching, you could also send a cheap talk message that says, oh, and the edge is MU to MD. Okay? If you really wanted to directly map it to this. And the same thing here. With probability of 1/2, you would say this MD state is matched with the RD state. You're going to reveal that the Y dimension is D, recommend acceptance, but you could also say, yeah, and the edge is over here. Now, you don't have to give this extra cheap talk message because, well, if by giving it all of the obedience constraints are satisfied, then without giving it, we're just summing up over these constraints, and so that it'll still be satisfied. And so that's why you don't need to have the cheap talk. But if you wanted to very literally map it to the graphs, I don't know. We thought it was helpful. If it's not, we can remove it too. It's not necessary at all.
I see.
It's descriptively useful, but not necessary. We can integrate them out.
I see. And then in the model, the sender makes a commitment. Did you talk at all about why we should think this assumption would be plausible, or in what settings it would be plausible?
No, in fact, we came at this problem from wanting to study incentives. And so I had this short example on incentives. I think in some cases you could argue it is plausible. So you could argue, for example, one of the applications might be to research design. And so, what's a fact? The result of a particular regression. How much you get commitment? Well, if you have to pre-register a study that sort of says, here's the data I'm going to collect, here are the regressions I'm going to run, then you're sort of committing to presenting results on a particular set of regressions. And so maybe in those settings, there's quite a literal commitment. I think for us, though, it's quite helpful as a benchmark. And of course, in environments where subversion is possible, commitment has no bite. The commitment and no commitment outcomes are the same. But yeah, I think there are certainly settings, applications where commitment makes sense here, and others where maybe less so.
I see. And just to circle back, then in the no commitment setting, are the cheap talk messages important?
No, you could do the same kind of integration. What is important, which I didn't have time to talk about, and is not in the version of the paper you read, what turns out to be important is whether I have to reveal at least k facts in these Cartesian models, or I can reveal only exactly k facts. Without commitment, I can sometimes get a little bit closer to commitment by sort of revealing a lot of information to you. And if that's possible, that can be beneficial depending on the settings. But the extra cheap talk messages are not,
I think it's a good time to close this